Hola, hola. Bueno, hola a todos. Hoy estamos en un nuevo coloquio del Departamento de Física. Tenemos una invitada internacional que es Nathalie Ouellette. Ella está trabajando en la Universidad de Montréal, es la spokesperson del proyecto James Webb. Nathalie estudió física, después se especializó con un doctorado en astrofísica y en algún momento cambió un poco su carrera a hacer divulgación de resultados y a trabajar con los equipos científicos en la divulgación de resultados. Así que bueno, le agradecemos muchísimo a Nathalie su presencia. Now I'm switching to English. Thank you, Nathalie, for being with us today. Well, she was very kind and accepted to give this conference to show us the last results from James Webb Telescope. She's working there in Montreal with several researchers who are doing top research in the extragalactic astronomy and also in exoplanetary physics. So, well, I let you all with Nathalie. Thank you for being with us today.
Hola, gracias. Hablo español solo un poquito. Mais je parle français très bien, but I will do this in for English, so I'm not going to try to go into 3 different languages. But yeah, it's my great pleasure to be with you virtually today and talk to you about some of the great things that the James Webb Space Telescope has been doing. So I'll go ahead and share my screen now. Lots of stuff to go over. I'll ask you to keep your questions for the end, if you have any, because sometimes I answer them along the way. I think that makes the most sense. So astronomy. Astronomy is a science that a lot of people love. I think that we have a lot of benefit, privilege, but also responsibility as astronomers to do a lot of outreach, just because it is such a popular science with the general public. It really captures people's imagination. And I think space telescopes is something that really captures people's imagination. And we've seen that recently. It's a very old science. We've been doing it for the beginning of time, essentially. But we've been building tools to do this better. And what I always like to mention is that, yes, our tools like telescopes allows us to look at fainter objects, farther distances, but also for the very longest time, we as astronomers have been constrained to looking at visible light. But as we know, the electromagnetic spectrum is very, very rich in all kinds of light. And even though humans can only see the visible light, the universe is talking through its phenomena in all the different kinds of light. So in order to look at all these different kinds of light, we have to have different tools, such as telescopes honed for these different parts of the electromagnetic spectrum. Now, what is the universe saying at all these different kinds of light? So depending on which type of light in the electromagnetic spectrum you're looking at, you're seeing different components of a celestial objects, different phenomena that are going on. So this is an example. This is the Whirlpool galaxy here, a very classical spiral galaxy. And you can see what it looks like looking in the radio, infrared, optical, ultraviolet, and X-ray. And you'll see different parts of the galaxy illuminated depending on the light that you're looking at. So of course, infrared, optical, ultraviolet, we're looking mainly at the stars, but different populations of the stars based on their temperatures and their size. X-ray, you're looking at very, very hot gas and a lot of activity surrounding the supermassive black hole at the center. Radio, you're looking at the cold gas, which will maybe eventually turn into stars through stellar formation. So in order to have the complete picture of what's going on, you must, of course, look at all types of electromagnetic spectrum, all types of light. So all of these different telescopes are really working conjointly, not in competition. Ideally, a single object will have observations in all different kinds of light. But of course, as you might know, we live on Earth where there is a protective atmosphere that blocks out many of these types of light. So this shows the transmission percentage of different types of light for the Earth's atmosphere. And you can see there's a very nice window in the visible, there's a very nice window in the radio, a little bit comes through in the near infrared, although with the tellurics in the Earth's atmosphere, there's a lot of contamination there as well. So for some types of light at very short wavelengths and in many parts of the infrared, you must go to space. So I asked, where's the best place to put a telescope? We know that there are telescopes all over the world, all over the Earth. Many of us have the chance to go visit them for observing missions. But the best place to put a telescope in many regards is space. There are disadvantages, of course. It is expensive to send something to space. It is also very risky. When you put something in a rocket, you don't know if it will get there safely, and if it breaks on the way or if it breaks during its operations, it can be difficult or even impossible to fix. So it is very important to have both complementary ground-based observatories and space observatories as well. So you can't talk about space telescopes without talking about the Hubble Space Telescope. Hubble being a visible light telescope launched in 1990, led by NASA with a strong European component as well, and Hubble had a rough start. Hubble had defects in its optical system, in its mirror, and so the very first images that came from Hubble were quite blurry. In 1993, there was a servicing mission using the first Canadarm. So I am based in Canada right now. It is our robotic arms are some of our great pride and joys. And so in 1993, thanks to the work of the Canadarm1 and astronauts, the Hubble Space Telescope was repaired and has since been doing wonderful science and also wonderful public outreach work through the beautiful images that it's created. But it is an older telescope. You might have seen in the news in the last few years, it has had to go through safe mode. Some of its instruments have failed and have been replaced over time. There are currently no future servicing missions planned for Hubble, although SpaceX has shown some interest in trying to keep it going. But since the mid-1990s, we have been planning for the successor of Hubble, not the replacement. Again, we're hoping that both Hubble and the successor, which is the Webb Telescope, will work conjointly for as long as possible. So in 1995, this idea of a very, very large infrared telescope, at the time named the Next Generation Space Telescope, was created. And there were many reasons to go into the infrared, one of which was to look at the very earliest galaxies in the universe. And I'll mention that a little bit later when I talk about the scientific goals of this mission. So this was led by NASA with the European Space Agency, who were the two partners in Hubble. But here in Canada, we're overjoyed to say that the Canadian Space Agency also has a very important component to this mission. It's the largest space astronomy mission Canada has ever participated in. And I hope that it is a blueprint that we will recreate in the future with other large space telescope missions, including maybe a UV and blue light telescope called CASTOR that we are hoping to lead in the next few years. It's still under development, it hasn't been funded yet, but it's something that we're pushing a lot for. And if you're interested about the CASTOR telescope, you can ask me more at the end of the presentation. So I am the outreach scientist for the Webb Telescope in Canada. Outreach scientist is a position that is starting to be more common, but for the longest part, it hasn't really been a field that has existed a lot. Science communication is in full bloom now. It used to be that people in charge of communications were people who had journalism backgrounds or education backgrounds, but now many people, such as myself, have a science background, get a PhD in a certain science, and then end up working the outreach side of things in these very important missions. So my role is to act like a bridge between the science team and the general public to make sure that everyone knows what's going on with the telescope and get to benefit from all the wonderful discoveries that are ongoing. So this telescope, which has been in development for a very, very long time, finally launched almost a year ago now, it's hard to believe, on December 25th in 2021, so Christmas morning. And many people were supposed to be all over the world for this momentous launch. Maybe you got to see it live online. It was live streamed. Luckily, we still had a few Canadians at the launch site. It was launched from Kourou in South America, in French Guiana. And so this was one of the contributions of the European Space Agency, an Ariane 5 rocket, which launched the telescope in space. So here you have René Doyon, who is the principal investigator of the Canadian instrument aboard Webb. Here you have Begonia Vila, formerly an astrophysicist, now an engineer. She worked at Honeywell, the main industrial partner for the Canadian instrument, while it was under development, and now works as an instrument engineer with NASA. So she's still on the mission. And this is Dave Aldridge, who was until very recently with Honeywell Canada as well, and helped with the development of the Canadian instrument. So we had a few Canadians on site. Most of us, unfortunately, had to cancel our trips and had to watch from home because of the Omicron wave of COVID. So this is the launch. I believe there will be sound here, so I will just take a few moments so that we can relive the launch together.
À tous de DDO, attention pour les deux comptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
So this was a very emotional moment for the team. Many people had spent their entire careers working on this telescope, and to finally see it launched, and in the year following it, do the commissioning and now have its scientific operation starting, it was really fantastic. The launch went remarkably well, so well, and the subsequent trajectory of the telescope, that we saved a lot of fuel during this launch, which allowed us to prolong the estimated lifetime of the mission from 10 years to 20 years. So a really, really well done launch. Of course, the launch is only the start. So on top of it being a wonderful scientific instrument, Webb is also a technological wonder. It is the largest space telescope we've ever sent into space. Its mirror is 6.5 meters wide, and its largest component, its sun shield, is about the size of a tennis court. So I like to say that the whole observatory is about the size of a small house. So even though the Ariane 5 rocket that launched it is one of the largest rockets in operation, who could have such a large payload, we knew right from the start that this telescope couldn't simply be housed within the fairing of the rocket without us having to fold it on itself. So this was a very early part of the development of the telescope, making sure that it could be folded up and then subsequently deployed after its launch. So after launch, the fairing of the rocket peeled off and then started a 14-day-long deployment sequence. And if you followed this a little bit, it was very nerve-wracking. Again, it went perfectly well, but there were over 300 single points of failures in this deployment sequence, which means that there were over 300 ways that the mission could fail without us even getting to start. Of course, there were redundancy systems, but not an infinite amount. And this was all happening as the telescope was moving towards its final destination in orbit around L2. So here you're seeing one of the critical points, the deployment of its sun shield. Now, because the Webb telescope is an infrared telescope, it is very critical to keep its mirror and its instruments on the cool side of the telescope at cryogenic temperatures. So in this case, about 40 degrees Kelvin. So we can achieve this through only passive cooling by blocking the sunlight. So this is 5 layers of a very reflective material. And this allows the great majority of the sun from touching the mirror and the instruments. You also have the mirror here, which has petals on it. So it's a total of 18 segments. Each is about 1.2 meters wide, and they can all be moved independently, which allows us to align and modify the shape of the mirror slightly. And they're covered in gold because gold is very reflective for infrared light. So after 14 days of deployment, there was an additional 2 weeks or so to reach its final destination, where it reached its final orbit around L2, Lagrange 2. So it is always almost directly behind the Earth. If you trace a line between the sun and the Earth and Webb, the point actually goes, the line goes through L2. And so Webb is always oriented such that it has a cool side where it is hidden by the sun shield from the sun. And that is where the mirror and the instruments are located. On the other side, the sun side, sun-facing side, you have the solar panels and the communications array on that side. So this is where it is. It is on about 500,000 kilometer orbit around L2, and its orbital period going around there is about 6 months. So It stays there without much effort, but every 3 weeks or so, it requires a mild course correction in order to keep it stable on its orbit. So there are 4 science instruments located in an instrument module at the back of the mirror. These are the 4 here, all combinations of detectors, spectrographs. All told, it's 17 different modes that are enabled by these 4 different instruments that allows to observe many different types of objects for many different scientific goals. So NIRCam has been a crowd favorite because it's been taking a lot of the beautiful images that we've seen. It also has a coronagraph on it. It has coronagraphic capabilities. NIRI also has spectroscopic and photometric capabilities and coronagraphic capabilities looking in the mid-infrared. So it has an additional cooling mechanism to bring its temperature down to 6 or 7 degrees Kelvin. NIRSpec, very powerful spectrographs with a micro shutter array on it. And NIRISS is the Canadian instrument, but it is actually a double instrument. So this is the Canadian contribution to the mission. It's about the size of a washing machine. And initially, we were only supposed to have a guiding camera as our contribution, but we were able to do it and add in another component below it. We had the weight constraints for it. So the fine guidance sensor, the guiding camera, allows the telescope to lock onto its targets. So even though it is not a scientific instrument, it enables every single image and observation taken by Webb. So I always like to say the International Space Station has a Canadarm, and the Webb Telescope has a Canadae. So we're very proud. It was a lot of responsibility, but it's been working remarkably well at a level of 2 to 3 times better than we had planned for. So very, very happy about that. On the underside, you have the near-infrared imager and slitless spectrograph. There are 4 different modes on it. So imaging is more of a supporting mode for the other modes. You have the WFSS, WFSS mode, which is wide field slitless spectrograph, which allows the simultaneous collection of hundreds of spectra from different objects. So very, very good for looking at galaxy clusters and many members. You have the SOSS mode, SOSS, which is a single object slitless spectrograph. Very good for looking at transiting exoplanets to do transit spectroscopy and try to figure out the composition of their atmospheres. And the final one is AMI, or AMI, aperture masking interferometry. So we have the capability of using a mask inside of the NIRISS instrument to do interferometry and getting real pseudo images of protoplanetary disks, brown dwarf companions, all kinds of really amazing things. So the maestro for the Canadian contribution was, of course, the Canadian Space Agency. But the main academic partner was the University of Montreal, where I work at the Institute for Research on Exoplanets. We also had people from other universities working on this as well. The Hertzberg Institute, which is a national agency for research. We have a specific institute for astronomy. It's in Victoria in British Columbia. And Honeywell Canada, based out of Ottawa, which was the main industrial partner. But all told, hundreds of people in Canada, over 10,000 people globally contributed to this mission. So this is the University of Montreal team as of 2021. It's something that's been evolving over many decades, of course. So this is a picture that we took shortly before the launch last year. And one thing that I always like to mention is there are many young faces here. So many of these people are graduate students who have been doing simulations, preparing us for receiving data, have been doing some calibrations on the instruments, and many of them are actually leading very important observing programs during the first year of observations for Webb. So very exciting. I can't even imagine what that would be like. My PhD thesis is on some of the first data coming from Webb. So very bright students, and I'm very glad they're getting to enjoy some of the very first data from Webb. So what has the telescope been doing since we launched it last December? It's been doing lots of things. So after the launch, as I mentioned, it took 1 month to deploy and get to its final destination around L2. Then we entered the commissioning period, very important. We turned on all of the instruments, make sure that they were science ready. That step was completed. We declared everything was science ready in early June, mid-June. But during that moment, we had also a very important step to align the segments on Webb's mirror. So I mentioned Webb has 18 different segments that can be moved independently. So when we first opened up the camera on the telescope, and NIRCam was doing a lot of this work, we use a very bright star to do the alignment of the mirror. So when we first opened up and took an image of that star, we didn't see one single star. We saw 18 points. That's because all 18 segments were working independently, were not well aligned. So this is the image that we saw here. So the first thing we needed to do when we took this image is that we needed to identify which of these star images corresponded to which of the different segments. So here, all the different segments on the Webb telescope have their own code, and we're able to identify which image was taken by which segment of the mirror. Then we can start aligning, moving those different segments to at least place them in a configuration such that the images of the star that we took is in the same configuration as the segments. So this was the first step here. But you will notice, however, that these different images of the stars are ellipsoidal. They're not nice point sources, so they're kind of smeared. So the next step that we need to do then is we need to make sure that all of the different segments can actually focus on the star and really have a sharp point source detection. So everything gets sort of like brought down to a sharp point, higher resolution. So this is the next step. But of course, we sent a very large telescope with a large mirror up there so that it can work as one single mirror. We don't want 18 small mirrors. So the next step is to, again, moving all of the different segments on Webb, aligning them so that all of the different images of the star are stacked to create one single image at the very center. So this is what you see here. And then you'll see the point spread function. We want to make that point spread function as sharp as possible. You'll see that in a moment. And once that happens, you know that all of the different segments on the mirror are working together as a team, as one single unit. And we finally have a 6.5 meter telescope working properly. So that's fantastic. We still have the flexibility of moving those different segments independently, which is very reassuring. If ever something happens, there's damage, one of the segments fail for whatever reason, a micrometeorite hit, for example, we can then move those other segments to compensate for that damage. So it gives us a lot of flexibility that we didn't have for the Hubble telescope. You might have noticed also another signature of the Webb telescope's mirror. In a lot of the images you might have seen, there's a very particular diffraction pattern on the very bright objects, such as stars, that we see in the images. So essentially, this is a really nice infographic. I won't dwell on it, but it's on the Space Telescope Science Institute website if you're interested. But the 6 big spikes, 2 little spikes, that is a signature of the shape of the mirror. So every telescope has its own signature diffraction pattern. So that is a very specific diffraction pattern that is due to the strut and the shape of Webb's mirror. So after we aligned, we started taking images to make sure that everything looked good, everything was high resolution, very sharp focus. And this is a comparison that we did with the Spitzer Space Telescope, an infrared telescope that is now retired, that was nearly 100 times smaller than Webb in terms of the surface area of its mirror. So these are close to the same type of color, same wavelength in infrared. And you can see, looking at exactly the same part of the sky, what Spitzer can see and what Webb can see, it's quite different. So the stars are much sharper. You can see detail, structure, texture in this nebulosity right there. And you can see many, many more stars in the background as well. So this was just a proof of concept, and it shows that the Webb telescope is a huge step forward in astronomy in general, but certainly when you're comparing it to previous infrared telescopes. So now, science. This is all sort of like the technology that was driving the development of Webb, but we want to do science with it, and we have started doing science with it. So we can categorize the 4 different scientific goals of Webb into these 4 categories. The first is alien worlds. So these are objects within our own solar system, basically everything that is beyond Webb's own orbit towards the edge of the solar system. So Mars, all the planets except Venus, Mercury, and the Earth. It can't look at the sun or the moon either. But also near Earth asteroids, comets, trans-Neptunian objects, and also, of course, exoplanets, a very, very big component of Webb's scientific mission. Also the life of stars, going from star-forming regions all the way to the death of stars and the stellar remnants that result in the death of stars. We want to understand the evolution of galaxies, looking at the local group, nearby galaxies, all the way to through cosmic noon, all the way to cosmic dawn, understanding all these different steps of galaxy evolution. And speaking of cosmic dawn, one of the main goals of the Webb Telescope is looking at the very early universe. So we want to push back how far we can see in terms of distance, of course, but in terms of how close we can get to the Big Bang. So the Hubble Space Telescope managed to look up to about 500 million years after the Big Bang. With Webb, we are hoping to push that to 200 to 300 million years after the Big Bang. And it was a very, very busy time in the early universe. So a lot can happen in those few 100 million years difference. And it seems like we've already managed to do this because in some of the images we've taken with Webb, we calculated the age or the redshift of some of these galaxies. And it looks like we're beating records and we're seeing as far back as we were hoping with the telescope. So we'll be looking through some of the first images that has come out of the mission together. The first is not an image, it is actually a spectrum. So this is in the category of observing alien worlds. So this is an exoplanets. And this was the first image that we revealed for the Canadian instrument on July 12th, when all the first images were revealed from the James Webb Space Telescope. So of course, when we want to observe an exoplanet, even though we can do a little bit of direct imaging, and I'll talk about that in a moment, mostly what we can do is indirect measurements of exoplanets. It's very hard to spot them. We can't really take pictures like this, like we can for planets in our own solar system. So here at the Institute for Research on Exoplanets, we try to cover all the fields of exoplanets. We do theoretical work, observational work. We also do instrumentation development to help us gather the data that we need to do exoplanet science. So we're over 60 people spread over 5 different institutions in the province of Quebec. Many people are very actively involved in Webb and Webb programs for exoplanets. So the way that we spot an exoplanet, typically it's an indirect method. And the most common of these methods is the transit method. So this is when an exoplanet passes in front of the disk of a star, and then you have a dimming of that light. And if that dimming is periodic, you have a good indication that there is something passing in front of that star on an orbit. And so depending on the depth of that dip, you can also tell how big that exoplanet is. But typically, it is the sort of opaque, more solid part of an exoplanet that blocks out that light. When you have a transit occurring, you can have an atmosphere around that exoplanet, which does let some of that light pass through. So this is a transit light curve that was observed for the planet WASP 96b, a hot Jupiter, over 1,000 light years away. And as it passed in front of its planet, it blocked out that light, as you can see here. This is a raw transit light curve, so very, very clean. We were all just amazed when we saw this data. Webb data is so amazingly clean. But what happens here is the starlight will still stream through part of the exoplanet atmosphere and will be absorbed at specific wavelengths. So the spectrum that you collect will have absorption features that match certain elements or molecules that are found within the atmosphere of the exoplanet. So we get a resulting atmosphere spectrum. So this is the atmosphere composition, the spectrum for WASP 96b. And so here you have the amount of light that's blocked. Some people do it the amount of light that you see. So you can have either absorption features as dips or absorption features as bumps, depending on how you do it. And you can see this is all in the near infrared. So we had a very clear detection of water vapor in this case. Now, this is just a confirmation of water vapor detection. Hubble had seen this previously. We did, however, see proof of haze and clouds, which was previously thought to not happen on this particular exoplanet. So it was not necessarily groundbreaking in terms of the discoveries, but it was groundbreaking in terms of how good the data was. So it was just the first proof of concept. We were very happy. Hot Jupiters are quite easy targets, but we are doing the same exercise for many other exoplanets, including Earth-like planets, such as the ones in the TRAPPIST-1 system. Now, moving on to the images now, many of you, I'm sure, have seen the Carina Nebula, or even it's the wallpaper on your laptops. I've seen a lot of people change their wallpapers recently. So the Carina Nebula, it's a star-forming region in the Carina Nebula. This is a zoom in here of a region that you can see in Spitzer. And we took it in both NIRCam and in MIRI, so both in the near and the mid-infrared. So looking a little bit closer here, you can see a huge amount of detail. That is the thing that has sort of come out the most when we've been looking through these images. Just the sheer amount of detail that you find in these images. Seems like every single pixel is just full of science that you could do there. So you can see lots of structure and texture within the what we call the cosmic cliffs. And one of the reasons is because this is looking at infrared light. So infrared light passes through cosmic dust, whereas cosmic dust blocks out visible light. So because we're looking at infrared light, we can peek into some of these areas of cosmic dust where newborn stars are being created. So you can see here these golden little features right there. This is a newborn star that's being born. This is a newborn star that's even, you can see its protostellar jets coming out right there. This is just in the first few million years of these stars' existence, which is typically a very difficult time to study these stars because they're still enshrouded in dust, and that dust tends to block out light. So this is a very, very special moment in the existence of stars that we're able to capture using the Webb Telescope's capabilities. You can also see cosmic dust that's being carved by stellar radiation from some of these newborn stars. So lots of interaction throughout the stellar forming region with these different stars at different stages of their early lives. So here, this is an example of the power of infrared, the same part of the Carina Nebula as seen using the Hubble Space Telescope in the visible and the Webb Telescope in the infrared. So lots more detail, and you can see through much of that cosmic dust using infrared light. Now, from the birth of stars, you can also look at the death of stars. This is the Southern Ring, a planetary nebula. So this was caused by the death of an average star, a sun-like star. So at the end of a life of such a star, it puffs up into a red giant, expulses, ejects its outer layers of gas and dust. And so this is what you can see here. These layers are layers of gas and dust that have been expulsed from that star. And what you have left at the center, the stellar remnant or the stellar cadaver, is called a white dwarf. Now, many people, when I show them this picture, they might think this is the white dwarf because it's the only star that is visible in the near infrared. But the same celestial object was observed in the mid-infrared as well. And this shows the power of using different kinds of light even within the infrared. So here in the mid-infrared, you see that it's actually a binary system at the center. Yes, the very bright white star is still seen there, but you can now see a red star. And that red star, despite it being red, is actually the white dwarf. This white dwarf is quite young and is still enshrouded by layers of gas and dust that it has been expulsing. And this layer of gas and dust is being heated up by the white dwarf and is radiating itself in the mid-infrared. So mid-infrared actually is great to capture radiation or light emanating from gas and dust especially itself. So very, very nice that you can only see this when you're looking at the mid-infrared. So there are actually two stars there. The white dwarf is not the one that you might think. And another thing that we love about these images, no matter where you look, no matter what the main star of a picture is, there are many background galaxies all around. So this is an edge-on, almost perfectly edge-on spiral galaxy that you can see as a single line there, but you can see many other galaxies spread out in the background there. Speaking of galaxies, this was another image that we released, Stephan's Quintet. So this is a group of 5 galaxies, 4 of which are interacting. And they are all interacting, harassing each other in collision. You have these two here that are in mid-collision, and this one that's heavily being interacted with by this group there. So this is an image both in the near infrared and the mid-infrared. You can see, even though a collision of galaxies can be a quite destructive phenomenon, when the two different galaxies are in collision, you have their gas envelopes, their gas content that's colliding and also being compressed, which causes bursts of star formation. So these gas shock waves will actually lead to the creation of more stars later on. If you look in the mid-infrared, however, you can still see more sort of hidden goodies. By looking at the mid-infrared, stars don't really shine very much in the mid-infrared. Here you're seeing mostly the gas and the dust within the galaxies. So I like to call these gas skeletons. So it's sort of like taking an X-ray of a person, but you're taking an X-ray of a galaxy. And these gas skeletons will eventually turn into stars through the process of star formation. You can also notice that this top galaxy right here has a center that is much brighter than you could initially see. And that is because there is a really big black hole or a supermassive black hole at the center there. So that supermassive black hole is actively accreting material. It has an accretion disk, and that accretion disk is being heated up and shining very brightly in the mid-infrared, which is why you can see it so brightly in this image right here. But you don't only need to see it in an image. We also took some spectra of the active galactic nucleus, or the active black hole at the center of that galaxy, and we were able to determine some of the composition of its accretion disk. So we were able to look at the accretion disk around right there, and we found strong signatures of silicates. So sort of like very, very fine sand, like you might find on a beach, but even finer than that. That is the material that the active galactic nucleus is actively feeding on. You can also measure the speed or the velocity of the jet that is being shot out of the AGN right there. So here you can look using redshift, or a form of Doppler shift. You can look at the velocity, and we're looking on average on the order of 200 kilometers per second, how fast gas is being ejected from this AGN. Now, the final image that was released during those first few images on July 12th is the Webb Deep Field of Galaxies. This was an observation taken by all 4 instruments. So SMAC 0723 is the name of the galaxy cluster observed here. It's the galaxies that are larger, more white. You can see them spread out here. But of course, you can see many, many galaxies in the background. So there's about 7,000 galaxies found within this image here. And many of them are actually behind the galaxy cluster that we're observing. And you can see many different colors, and many of these galaxies are at different stages of evolution as well. So you might have heard of the Hubble Deep Field and the Hubble Ultra Deep Field. Now, those images were actually taken over the course of many, many days, whereas the Webb Deep Field was only taken over the course of 12 hours or so. Even so, you can see in this comparison picture that we saw many more galaxies, and partially that's because of redshift. So the very, very distant galaxies were shining in blue and ultraviolet light, but as they were pulled away from us because of the expansion of the universe, their light has been shifted, stretched out, and shifted into the red and the infrared, which is why we knew we needed an infrared telescope in order for us to look at these very distant galaxies. So a lot of those galaxies, they required infrared. The Hubble Space Telescope couldn't look at them. If we look closer in, however, we actually took some spectra of some of these galaxies. So yes, we've observed galaxies as old as this, but we've never been able to take a spectrum of such a galaxy that's 13.1 billion years old and actually take a high resolution enough spectrum to start determining some of the elements found within it. So you can find oxygen, hydrogen, and neon lines within this tiny little speck that is 13.1 billion years old. So a very, very distant galaxy. You can also identify the redshift or the age of these galaxies using the spectra as well. So you can, using NIRSPEC here, and the microshutter array mode on NIRSPEC, we detected and we calculated the redshift of many of these different galaxies. And if you take a closer look, you might notice that some of these galaxies look a little bit weird. So here you can see that they've been deformed through gravitational lensing caused by that galaxy cluster that is between us and the distant galaxies. So here, this is a single galaxy that has been stretched out and created a double image. You can see some other galaxies there and there. And this is a galaxy that I'll mention in just a few moments. It has been lensed. We actually had a triple image of it, and we have some really cool results about that. So how do we know that this galaxy and that galaxy is the same one? So obviously we can take a spectrum of both of those galaxies, and if the spectra match, we know that they're the same galaxy. So this was done using the NIRISS instrument, so the Canadian instrument, and this is how we can tell that it's a double image of a single galaxy. So this little galaxy that I mentioned just a few moments ago, we called it the sparkler because when you're looking closely at it, it's stretched out, but you can see all these little bright dots spread out around them, around the galaxy. And so it was triply imaged. So we knew, because we saw the sparkles around them at the same place every time we saw an image of it. And so we knew that they were not just another object that was between us and the galaxy, they were really a part of that galaxy. And if you compare to the photometry that we had of that galaxy with Hubble, you can see that we wouldn't have been able to do this kind of science using Hubble photometry. So this is a recent result that came out just last week by a Canadian team led by two postdocs at the University of Toronto, Lamia Maula and Karthik Iyer, and many other people of a collaboration called Canucks in Canada, working on very distant galaxies. And they were able to identify these sparkles, these bright points, as globular clusters, we believe. So using photometry, they were able to get the age of some of these individual sparkles or globular clusters. And this galaxy is about 10 billion light years away. And so the fact that we found these globular clusters to be 3 to 4 billion years old indicates that these are likely the oldest globular clusters we've yet to discover. So very exciting. And Canucks will be doing similar studies on other distant galaxies as well. So if you're interested, it's Maula et al. 2022 to look more into this really cool result. We've done lots of other imaging as well. I can mention this picture of Jupiter. We can see auroras, rings, moons. I'm running out of time, so I'm just going to go quickly through these. I do like to mention for this image, it wasn't processed by anyone from the Webb team. It was actually processed by Judy Schmidt, who's a citizen scientist, a young student in California, not in astronomy, and she has been teaching herself how to do image processing using Hubble data for the last 10 years, and she created this beautiful image. So a lot of Webb data is publicly available to anyone who knows how to use it, wants to learn how to use it, and she created this image here. Mars also had some observing time. It had a special guaranteed time observation program. So we did some photometry, some imaging of the surface. We also took a spectrum of its atmosphere, and we spotted some markers that we knew were there, of course, CO2, some water, some carbon monoxide as well. This has been my favorite image that has come out of the solar system objects for Webb. This is an image of Neptune. You can see Neptune and its very ghostly rings there. 7 of its 14 moons. Its most major moon, Triton, is actually brighter than Neptune here because Triton has an albedo of about 75%, so very reflective, whereas Neptune has a very high methane atmosphere, which is actually absorbing a lot of infrared light. Nevertheless, this is the best image we've had of Neptune in about 30 years, over 30 years, since we've had a Voyager 2 flyby. And if you know about the DART mission, we sent a satellite to smash into an asteroid to see if we could deviate it on its orbit. Both Hubble and Webb and many other telescopes have been doing follow-up observations of that impact to look if there's been a difference in its orbit and try to better understand the composition of the asteroid as well. So lots more images, and there will be more coming out. The Cartwheel Galaxy here, a ring galaxy that was the ring of star formation around it was probably caused by a recent interaction with a nearby galaxy. The Tarantula Nebula, found in the Large Magellanic Cloud, the highest star-forming region in our local group, so very, very active star factory. And one last result that I can mention that is close to home here at the University of Montreal. This was released a little bit over a month ago. This is WASP 39b, another hot Jupiter planet 700 light years away, that was observed very early on in Webb's observing program. And this study was led by Nathalie in the US, but we also have a component here at the University of Montreal where we did a lot of our data analysis as well. So these are my colleagues here who worked on this group, and they observed the very first detection of CO2 in an exoplanet. So this is the transit light curve again, raw data. You can see that it is a very clean spectrum. There's no denying that a transit is occurring there. And you can produce this atmosphere composition spectrum right there. So this carbon dioxide detection is actually a 26 sigma detection. So in science, when you've got 3 sigma, you're happy. When you've got 5 sigma, you win the Nobel Prize if it's a new detection, of course. 26 sigma is like way more than is needed. But again, it shows how powerful this telescope is. And you might see also there's a little bit of a bump right here as well for another potential detection of another molecule. So there will be some other results coming out soon. So this particular spectrum came from NIRSS, but we also took a spectrum using NIRISS of the same exoplanet, WASP 39b, and those results will be coming out very shortly as well. The data is also exquisite. But this was a very exciting result, the very first time we've ever detected undeniably carbon dioxide beyond our solar system on an exoplanet. So I want to leave time for questions. I will end it there, but obviously it's just the start of the mission. We're hoping 20 more years of observations to do, and there will be a call for proposals this fall to try to find everything we're going to be doing for the second year of observations. So thank you.
Thank you, Nathalie, so much. So we were able to see, well, the great things James Webb is doing. I think while Gustavo reads, if there is any questions from the people in YouTube, I have one question regarding the observation of exoplanets. You were mentioning that it's very simple to observe the big planets, the gassy planets like Jupiter or things like that. And for example, in Saturn, we know that they are the satellites that have for example, the water or whatever. How is it possible with James Webb to identify the moon of a planet, from an exoplanet?
So we're only now starting to detect exomoons. There have been a few candidates in the last few years. We're definitely not at the point where we're able to do transit spectroscopy using an exomoon, but we use a technique called transit timing variation, or TTV. So we look at the transit of, so it's going to be something like this. We look at the transit of an exoplanet as it passes in front of a star, but sometimes we will see that the transit happens a little bit sooner than expected or a little bit later than expected. And in that case, it might be that there is a moon that is orbiting around the exoplanet. So depending on the location of the moon's gravitational pull might delay or rush the transit timing just slightly. So the first tentative exomoon candidates that have come out in the last few years have been using TTV as a method. So Webb would be able to, because it has such good data, it would be able to do follow-up observations and do TTV and try to confirm the existence of those exomoons. We would need something with better resolution and a bigger mirror probably if we wanted to start trying to figure out if those exomoons were potentially habitable. That's a little bit beyond what Webb can do, but it can help for detection of exoplanets.
Okay, and one more regarding exoplanets. It's out of the question to look for Earth-like planets for the time being, or it's planned that James Webb will be able to do that in the future, in the near future?
Not like right now. Like some of the observations of TRAPPIST-1 systems have already occurred, and we're working on the data analysis right now. We're hoping the results will be coming out in the next 6 months or so. And obviously there will be re-observations later on to stack orbits and everything. But definitely Earth-like planets is on the menu for Webb, and we're already looking into that right now.
Gustavo?
Yes, so we have a question in the YouTube at the moment. Let me read it to you. So it says, hi, Nathalie. Thanks a lot for the great talk. And the question is, does it make sense to take images of galaxy clusters such as the Ouellette cluster in order to improve our understanding on DM, example, self-interaction?
So certainly it might be of interest just because the James Webb Space Telescope has certain modes that allows taking spectra of many different objects at the same time. Dark matter is part of some of the scientific goals that Webb wants to study. I don't know of any current observing programs on the Ouellette cluster, but there's also like hundreds of observing programs scheduled for the first year, so I don't know them all by heart, but it's definitely something that might be done. Perfect.
And I have a question as well, which is, so you said you can determine like the age or the distances by looking at the redshifts. And my question is, how do you know the original wavelength from it is redshifting from? Like, is it a common wavelength for all galaxies, or?
So there are certain specific markers in galaxies, like the Lyman alpha forest, where we know where we're expecting markers at a specific wavelength. We also know a lot of the light emitted by galaxies come from stars, so we can sort of like tell what an average stellar population for a spiral galaxy, what that will look like. There are certain markers that we will expect in the emission. And so once we have that in a library, we can then try to match that to a certain redshift and match that to the observed spectrum that we do see. So there are models of galaxies that we expect in terms of emitted spectra, and then we match that to the observed one, and the difference is what gives us the redshift.
Okay. And about the mirrors that you had to do this positioning at the beginning, do you have to correct that often, or is it something that you did only once for alignment?
So it's not something that we want to do often. At the very start, we did an alignment for the central instrument NIRCam, and then we aligned it for all the other instruments. Now it works for everything. But people might have heard that in late May, there was a micrometeorite hit on the telescope that was more major than we had expected. The telescope still works fine and everything, but because it did cause some damage on one of the segments of the mirror, we did need to make an adjustment to the alignment to compensate for that damage and get the telescope back to as good of an alignment as we can get. So barring those kinds of unexpected events like a micrometeorite hit, we don't expect to have to realign the mirror often.
Okay, thank you. I think there is another question in the YouTube. It says, I wonder if there has been any insight respect to dark matter and dark energy issues.
So dark matter is something that could potentially be studied, as I mentioned. No results coming out up until now. Webb is a very diverse instrument, and dark energy could also be looked at, but I think the Nancy Grace Roman telescope that will be launched in a few years, it has two main goals: better understanding dark energy and taking direct imaging of exoplanets, and also microlensing for exoplanets. That will be a better tool because it will be really doing surveys to look at for example, supernova explosions to try and better understand the expansion rate of the universe. So Webb can help for that, but there were better tools suited that are coming up soon.
Thanks.
Creo que Hernán tiene una pregunta, Gustavo.
Okay, Hernán.
Hi, thanks, Nathalie, for the great talk. A pleasure to have you. Can you comment a little bit more on this citizen science project? How does it work? How do you instrument it? With whom do you cooperate?
So currently, with the example that I gave with Judy Schmidt, she is a citizen scientist, but she's very independent and she's learned to do this herself. So she actually just goes in and gets the fit files herself and deals with it. So not everyone can do that, of course. There is an astrophotography challenge that happens twice a year with NASA. One is going to be coming up at the end of the year, and we try to coach people in how to take data from NASA observatories and then do sort of like a rough image processing with them. So that is one option as well. In terms of less image processing, more actually doing science, we are hoping that Galaxies Zoo, which some of you might know, Zooniverse, Galaxies Zoo, it's classifying galaxies by morphology using huge amounts of data. We would like to have a JWST Galaxies Zoo component. So I've talked to some of the people at Galaxies Zoo, and we're hoping that that's something that happens in the future. So people can start classifying web images of galaxies by morphology.
Thank you.
Okay. Any more questions?
Great. I think for the moment there are no more questions in the YouTube.
Okay. Well, so we thank everyone. Thank you, everyone watching us in YouTube, and thank you, Nathalie, for being with us today.
Yeah, my pleasure.
Thank you. Hopefully, in a couple of years, you will be here giving a talk.
In person.
You have
good.
20 years to spoke of James Webb, so
That's right.
Thank you so much.
Have a good day.
Goodbye, you too. Bye.
Bye-bye.
Ciao, ciao.